Okay, so yesterday I promised you a little bit more time to work, so we're going to go through this bell ringer pretty quickly here. So it says a wave has a frequency of 15,000 hertz and a wavelength of 18 centimeters. What is the speed of the wave in meters per second? So you need to, in order to do this, in order to get this question, you need to have the right units, right? Because you want meters per second. So in order to get meters per second, you're going to have to convert 18 centimeters to meters. Just for the sake of seeing it, I'm going to show you what happens if you don't convert it to meters. What if I left it as centimeters? Okay, let's say I use the equation. So we know velocity is frequency times wavelength. So pretty simple. We just take 15,000 hertz. Or remember, hertz is seconds inverse seconds, times the wavelength, which again, what would happen if I left it as 18 centimeters? Okay, so you'd have 15,000 times 18. Okay, you get a big number. You get 270,000. But look at the unit. That would be centimeters. And if I put seconds, instead of leaving it in the top as -1, it would be +1 in the bottom. Centimeters per second. So that's not what I mean. If I want meters per second, that's why this doesn't work. But you could easily change it, right? So you could change centimeters to meters, right? Centimeters, get rid of it by putting it in the opposite place to meters. And of course, the conversion factor is 100 centimeters in 1 meter. That would give you meters per second. So then I take 270,000 divided by 100, and I get 2,700 meters per second. Okay, and that is the final answer there. Today is Thursday, so don't forget to go ahead, and I would do it right now. You should have put your answer in that bell ringer document sheet, that bell ringer answer sheet. Since today's the last day you have a bell ringer this week, you can go ahead and turn those bell ringers in. You can just hit submit, or I think it says submit or turn in on Google Classroom right now, and you'll have those in for the week. Okay, so today we're going to talk about something called the duality of light. Okay, we discussed electromagnetic waves or light yesterday. We talked about the electromagnetic spectrum. One thing I want to emphasize in today is that there are two natures to light. And those natures are light as a wave and light as a particle. And we can do experiments. You're going to look at two experiments today that show each of those, light behaving like a wave, light behaving like a particle. And both of those are true. So therefore, we have to accept that light is something that is more than just a particle. It's more than just a wave. It's some kind of combination of both. Okay, the first experiment to show this is called the double slit experiment. And so I just want you to think about this for a minute. So the way the double slit experiment works is you have light coming in, and then you have some kind of plate or sheet, something that would block the light, okay? But then you cut two tiny, tiny holes right in the middle of your plate beside each other. That's what makes it the double slit experiment. What would you expect to see on this other side? Okay? And you get there are, intuitively, I would expect, right? And I know the answer to this, but I still think that what I would expect to see if there were two holes here, I would expect to see those two things on the other side. Two little parts where it gets through, right? There wouldn't be anything here because light can't get there. There wouldn't be anything in the very middle because light can't get there. There would be a little bit of light here because light can get through, no problem. And there would be a little bit of light here because light can get through, no problem. And this would be true if light behaved like a particle. See, just like this. If light was like a particle, then okay, this light gets blocked, or it's gone. This light gets blocked, no, it's gone. The only light that can get through would be the ones that go right through that hole. And so I would expect to see this right here. But what actually happens is, since light, if light behaves like a wave, then after it goes through there, it'll start to spread out around these corners. Okay, that's called diffraction. So it start to spread out around these corners, and then the light would start to overlap those waves of light would start to overlap and interact with each other. And so if light behaves like a wave, we have, I'm going to talk about it more in just a minute, but destructive and constructive interference, and we would expect to see an interference pattern, which would look like these little stripes here. And I know this seems really weird, but I'll show you a visual in just a minute. I think will help make it more clear. Okay, so let's first talk about what is constructive and destructive interference. So waves have a special property that when similar parts of a wave overlap, they constructively interfere, or in other words, they add together to become bigger than they originally were. So you can see these two waves are going to be overlapped, and it's similar parts, right? You have the crest meet with the crests, and you have the trough meet with the troughs. And so what does that lead you to? Well, it gives you bigger crest. Again, these are taller than they would have normally have been, and deeper troughs. These are lower than they would have normally been. This is called constructive interference. Constructive because they build up. Think about construction. They build up together. But you can have the opposite. When we have opposite parts of a wave overlap, this leads to something called destructive interference, where they basically the waves cancel each other out. So notice here, I have the crest of a wave meeting with the trough of the other. And if you combine those together, this crest will cancel that trough and you'll be left with nothing. This is actually how, if you've ever heard of like a noise canceling headphones, like Bose is pretty famous for having noise canceling headphones. This is how they work. They take the sound, the ambient noise around you, and they basically play another sound, right? That's the weird part. I'm saying that they make it quiet by playing more sound. But the sound they play is inverted, right? So they try to take this ambient noise around you and play a sound that is the inversion of that sound. And that creates destructive interference where it basically cancels out, so there's no sound at all. Quite strange. I can take a sound, play an opposite sound. So again, I'm playing more sound. And if you hear one and the other individually, you would hear them perfectly fine. But when you hear both sounds together, they cancel each other out. They destructively interfere. It's pretty wild. Okay, I'm going to show you a video I think that will help clarify this a little bit. If you're watching this recording, I'm going to pause it here and you can watch it on your own. I'm not going to put that in the video itself. Okay, so this is just it's just a simulation. It's just a ripple tank simulation. We're going to look at the double slit experiment though. Okay, so imagine, let me see if I can increase the brightness just a little bit. Okay. So here what you have here is you can see up at the top, there's like waves being generated, and then here there are two small holes that the waves can travel through. In other words, double slit. So as these waves come out, I'm going to restart it so you can see. As those waves come out, they're going to interact with each other. And again, they're going to create constructive or destructive interference. And so what do we have here? Look, you have that pattern. There's a strong point in the middle. There's a point where there's almost no wave at all. This is where the destructive interference is happening. Constructive interference, destructive interference. So if you were to see this, it would be like a dot, blank, dot, blank, dot, blank, and so on. That's an interference pattern. Maybe if you see it, let me show you one more time in 3D so you can see. Might help a little bit too. That might be too big to be useful, actually. It's okay. Let me change a different color scheme real fast. That may help. Okay, maybe not. Let me take the brightness down. Maybe that'll help. Okay, let's try this one more time. Nope. Okay, sorry, it's not working very well. But the point is, the waves are interacting. They are constructively interfering in some places, destructively in others. And so you get this classic interference pattern. So the big takeaway here is that the double slit experiment shows that light forms an interference pattern, meaning that light behaves like a wave, right? Because once again, if light was a particle, it would just go straight through those holes. You would have those two spots on the back, and that would be it. But instead, as it goes through those holes, it diffracts around the corners, or it moves around the corners of that, spreads out, and those waves start to interact with each other and cancel each other out in some places, leaving destructive interference, adding up in some places, giving constructive interference. Okay, so again, big point, double slit experiment shows that light definitively behaves like a wave. Now we get to our second experiment, the photoelectric effect. So scientists discovered, around the end of the 19th century, so the end of the 1800s, that if you had a piece of metal, right, some kind of metal foil or something that was charged up, you could shine a light on it and it would lose that charge. Once we discovered a little bit more about atoms, we figured out that electrons were being emitted from that metal. And electrons have a negative charge, so as it emits electrons, it is losing negative charge. So you would give it some negative charge, shine a light on the metal, electrons would be emitted from that surface, it would lose that negative charge and get back to normal. Okay? This is called the photoelectric effect. But when scientists played around a little bit more, they discovered that the amount of charge sometimes wouldn't leave, right? So they found out that if you used a red light, it did not have enough energy to knock the electrons off of the surface. So again, I would charge it up, I would shine light at it, just like a lamp light or some kind of bright light, and electrons would start to leave the surface and it would lose its charge. So then a scientist does the same experiment, except instead of just using a light, they use a red light specifically, only red light. They shine it, and no matter, they can't knock any of the electrons off. It doesn't lose any charge when the red light is on there. So they say, okay, well, it makes sense that maybe red light doesn't have as much energy. We discussed this yesterday, right? As you go up the spectrum, the waves have more energy. So red light doesn't have as much energy as blue light, right? Some scientist does the experiment with blue light. They find out that blue light knocks the electrons off, no problem. Well, again, it's easy to explain. It's just energy. Red light doesn't have as much energy as blue light. So let's think about how would you, if you were going to use a red light, okay? If you're going to use a red light, how would you give it more energy? Well, you just make it brighter, of course. Get more light. Increase the amplitude is what we'd say in terms of waves. Increase the amplitude of the light. Make it brighter. So they did that. They got the red light, turned it up as high as they could. Still no electrons were knocked off. No matter how bright they made the light, no electron was ever knocked off of the surface. The charge was still held there. Okay, so they do the experiment with blue light. Of course, blue light, we talked about previously, knocks the electrons off, no problem. So blue light has lots of energy. How do we remove the amount of light, the amount of energy that blue light has? Well, we turn the light down. We make it really dim. And they found out that no matter how dim the blue light was, it still was able to knock electrons off. So this is quite a conundrum. Red light, no matter how bright, will never knock an electron off. Blue light, no matter how dim, will always knock an electron off. How can you possibly resolve this, right? Because again, if it's just energy to knock off the electrons. So if you increase the amplitude, you increase the energy. Why is it that they're not able to? The only way you can explain this is by assuming that the light is behaving like a particle here. So all the light, no matter how much light you have, is broken up into small particles we call photons. And a photon represents sort of an energy packet, okay? So whenever we shine this red light photons are always the same. If I increase the amount of light, if I turn up how bright it is, all I'm doing is increasing the number of red photons. But no red photon has enough energy to knock an electron off. On the other hand, you have blue photons. Blue photons have more energy than red photons do. And no matter how dim I make the light, if it's always broken up into little packets called photons, every blue photon has enough energy that it can easily knock off one of these electrons. Again, that summarized what I just said there. I'm going to show you a video. Again, if you're watching this not live, you can watch the video on your own. Okay, so again, photoelectric effect, that's actually what Albert Einstein got his Nobel Prize for, even though later he is more famously known for relativity, special and general relativity, but it's actually explaining the photoelectric effect is what kind of made him a rock star of the physics world, so to speak. Okay, so big question here is light a wave or is it a particle? The answer is yes. You can do experiments showing light behaving like a wave. We can also do experiments showing light behaving like a particle. It's something different. It's something more. It is something that has properties of both waves and particles at the same time. Okay, so that's where I'm stopping. There's an assignment on